Hey, good afternoon. So I'm going to pick up where we were last time, which is this notion of state machines having some redundant stuff in it, and in particular states which are equivalent. So kind of the idea being that we seek to reduce the number of states, and I guess therefore have less hardware and fewer smaller state registers. And intuitively, so I was walking through last time on kind of some notion of states, like how could we define equivalent states? So first notion was that if I look at two systems, then I can say, imagine the system were to start in state A or whatever state SI. And SJ. Okay, so this is a J. Okay, so imagine I take two copies of the same system, same hardware, and at t equal to 0, I start. Oh, it's not. Shoot. Oh, sorry. Okay, apologies. Again, we I'd introduce this notion that some states in a system may be redundant, as in if I can collapse them, I can they behave identically. And one notion of behaving identically is, imagine I take a system and I replicate it, and then let's say there are two states, one SI and SJ, which I believe are equivalent. So what I do is I start copy 1 in state SI and I start copy 2 in state SJ. And then I feed them the same input sequences. So same input coming in, going to both the copies. And then I'm examining the output of the two copies. And if they look the same, then it stands to reason that SI and SJ were equivalent, at least from no one can distinguish between them. And the problem with this approach, though, is I have to make sure that for all possible sequences X of any length, this property has to hold true. Now, that's not very realistic way to test for equivalence, but at least that's the property that we want. So that leads to kind of another approach, and that relies on this theorem, which basically says that the two states, that SI and SJ, are equivalent if, and this is a recursive definition, if for every possible input symbol, so let's say I'm in state SI or in state SJ, and I get some input symbol, right? Let's say some input symbol X. And if in both cases, it takes me to a state which is either the same state or again equivalent state. So let's say SI goes to state A and SJ goes to state B, then we say SI and SJ are the same if state A and B are in turn equivalent. Okay, so we kind of just and also outputs have to be the same. So that property has to hold true also. So for every possible input in my input alphabet, set of possible inputs, right? So we consume, I give the same token. So let's say possible inputs are 0 and 1, let's say. So then I say, if input is 0, SI and SJ produce the same output, and they go to states which are equivalent or the same. And likewise, we do it the same thing for input equal to 1. So now, why is this definition equivalent to the first definition? That's a trickier proof to do rigorously, but intuitively, at least it makes sense, right? Two states are the same. If for every input, they produce the same output, and they in turn go to an equivalent state. So that's the property we are going to rely on to give a method by which we can pretty efficiently get rid of states which are equivalent. So let's imagine I have this sort of horrendous looking finite state machine. Again, recall the syntax. So when we say like something like this, x/z equal to 0. So that means I'm taking that edge if x is true, x equal to 1, and output z is equal to 0. Usually when we have outputs on the edges, that indicates kind of finite state machine. So if output is written on the edge, then mealy, right? Because that means that it's dependent on the input. If it is more, I would be able to write it inside the node, because that means it only depends on the state. So now, having said that, sometimes people, when they, even if it's a more machine, they may just write it this particular way, because more is a subset of mealy in that sense. Okay, so I have this complicated looking state machine, and on the left hand side, we have the state transition table, right? So right hand side is the state graph, left side is a state transition table. And so here we see the present state, next state under the two possible inputs, x equal to 0 or x equal to 1. And likewise, I have the output for two possible input values, x equal to 0, x equal to 1. Now, looking at this, so our goal is, it seems like, if you look at it, that kind of the same combinations of x and z are occurring many times. So there are possibly some equivalent states. So let's see if we can begin to locate them. So if you look at state A and state H, you see that those two rows are identical, right? A and H under both x equal to 0 and x equal to 1 behave the same way. They have the same next states, C and F, and they have the same output 0 and 0. So these two states clearly are equivalent, right? They go to the same next state under the same next condition, and they output the same thing. So A and H are equivalent by any reasonable definition of equivalent. So we can get rid of those. And so I can, let's say, get rid of H, and then wherever H was occurring, what happened out here? Wherever H was occurring, I replace it with an A. So there was one such place where I scratch H, replace A, right? So now I have a modified table. Last row gone, and H replaced with A. Now we are going to play the same game again, which is, are there other equivalent stuff, any more equivalent states? So the trick at this point is that we are now going, so firstly, is there an obvious one out here? Are there two rows which are identical? Well, unfortunately, if you look at this table, there are no two rows which are identical for the next state and output. So the obvious equivalence is not there. But we still have that theorem that I mentioned there, right? The theorem basically said that two states are equivalent if their outputs are the same and the states they go to are equivalent. So now what we are going to do is we're going to look at pairs of states whose outputs are the same, because those are plausible candidates for equivalence. So in this particular case, we are going to look at those. So kind of from the table, if you see A and B, right, these two rows, right, their outputs are the same. When x equal to 0, both output 0. When x equal to 1, both output 0, right? So we are same here, same here. So they are possible candidates, but they are going to be equivalent only if C and D are equivalent and F and E are equivalent, right? That condition has to hold true. Our theorem said two states are equivalent if they have the same output under the same inputs, and under the same inputs, they go to the equivalent states. So A and B will be equivalent if and only if C is equivalent to D and F is equivalent to E. Okay, so I can rely on forming these kind of pairs. Now, in this particular case, let's look at C and D. Well, C and D their outputs are the same. So they satisfy that equivalence property, right? I mean, if I look at C and D, their outputs are same under same inputs. So that's good. And under X equal to 1, both go to G, which is equivalent. And X equal to 0, they go to A and B. But we are saying A is equivalent to B and for C to be equivalent to D, A has to be equivalent to B. So that's good. We are happy there, right? That we are kind of we are saying A and for X equal to 0, A is equivalent to B if C is equivalent to D, but C is equivalent to D if A is equivalent to B. So that part is good. What about F and E? Well, if I look at F and E, then again, for X equal to 0 and X equal to 1, they have the same outputs. So that's good. For X equal to 0, we are saying F is equal to E if F is equal to E. That's good. And we are saying for X equal to 1, F is equal to E, F is equivalent to E if A is equivalent to B. Again, we started by assuming that A was equivalent to B. So this seems to satisfy the set of constraints that A is equivalent to B if C is equivalent to D, but C is equivalent to D by circular argument, and likewise A is equivalent to B if F is equivalent to E, and that seems to be met as well. So in this particular example, this kind of multi-hop reasoning, right, going more than one step, kind of suggests that we perhaps we have a consistent solution out here. So let's work it through. So now I kind of did a hand wavy thing at this point. There is a very systematic approach that we follow. So it's called implication chart. And kind of the idea is we are making multiple passes over the state. So we're going to keep track of it. So what we do out here is in this implication table, we along the x-axis, we list all but one state, A, B, C, D, E, F. Okay, we skip G. And on the vertical part, we skip the first one and then include the last one, so B through G. So we create this kind of a grid. And now we are going to keep track of what is going to happen after each pass. Okay, so this is just a tabulation mechanism that we'll do. So what we start out with is after that first pass. So in each square, like let's say this square, we are going to write down the condition under which B and A are equivalent. And we'll write X if there's no way B and A can be equivalent. Likewise, let's say in this cell, we are going to write when C is equivalent to B, and so on and so forth. So let's start with like G and A. Now, G and A, they differ in their output pattern. So we can straight away put an X. They can never be equivalent. They are output different things. So we can go ahead and put X's wherever the outputs differ. Any two pair of states, if they have different values under the two output columns, they can never be equivalent. So there is a bunch of X. Let's verify F and D. So F is 0, 1 and D is 0, 0. Can't be. So that's why you have an X. So there's a bunch of X's that rule out some pairs. And then for the remaining pairs, we give the condition under which they can be equivalent. So let's look at D, D and C, right? So if I look at D and C, they have the same output, so that's good. And then G is equivalent to G, but A, B. So that's why you see it's basically saying D and C are equivalent if A is equivalent to B. So the stuff inside the boxes are giving the condition under which the equivalence would be true. So let's look at another example, G and F. So G and F is out here. They have the same output, so that's good. And then we are saying G and F are same if F is the same as C and A is the same as G. And that's why you see, sorry, did I mess up? FG. Let me just make sure about one thing. Let's wait. Just give me a moment. So D and B are the same if D is same as B and E is G, so that's good. C and B, okay, I'll come to this. I think I may have an error out here, but let's work through the others. So A and B, so A and B have the same outputs, and they will be equivalent if C is equivalent to D and F is equivalent to E. I look at these pairs. So that's what we have written out here, CD and EF. Then I look at C and A. So C will be the same as A if A is the same as C, which is given, and G is the same as F. So we just write that. And then C and B are the same. So C and B are the same if D is same as A and E is same as G. So that's what we get out here. F and E are the same if B is the same as A. So that we get. G is the same as E. So G and E are the same if B is same as G. That's here. And C is the same as E, which is out here. And then finally, G and F are the same. So G and F are the same if A is same as G, and why did I write E is the same as F? I must have messed it up. So this should say C is same as F. Did I repeat that mistake elsewhere? No. Okay. So this one seems to be wrong. It should say and if C is the same as F. Okay. So within each box, I'm kind of writing these two are equivalent if something else holds true. So I kind of do that. And then we are going to repeat this process. Now we are going to look at remaining states and see if they could be equivalent. So let's work that out. So what we do is at this point, we basically say, is it possible for things to be equivalent? Okay, so at this point, we look at our phase one chart that we created, and unfortunately, seems to be my mistake may have perpetuated out here. So, but let's look at this. So we basically look at these things and say which ones are not possible to be true, which ones can I cross out. So if I look at G and E, we are saying G and E are equivalent if C is equivalent to E and B is equivalent to G. But looking at this, we know that B can never be equivalent to G because in pass one, it told us an X, so we can rule this guy out. And likewise, this one gets ruled out because it requires A equivalent to G, and that is ruled out here. So by looking at X's, we can begin to rule out which one of the other boxes are never possible. So these two boxes go away, that it can never be the case that G is equivalent to E or G is equivalent to F. So let me pause out here. So pass one, we just go with question. For which one? E and G? Right. No, so if you look at this diagram, C and G, sorry, E and G. That's a strong, no, you can't say that, right? Because that all that would mean is B is the same as E and C is the same as G, but we are not saying that E. Let's see. So you're saying B is same as E and you're saying C is same as G, but that doesn't mean E is the same as G. No, but remember the requirement is under same input, they should go to equivalent states, not to themselves, right? Go back to our theorem. Our theorem says two states are the same if given a particular input, they output the same value, and they go to two states which themselves are equivalent. Okay, not that they go back to themselves. So looking at this diagram out here, E and G, for them to be the same, E has to be equivalent to C and B has to be equivalent to G. And that's why we had this condition out here. So we start out by phase one. We say that some equivalent, some two states can never be equivalent because their outputs are different, and the others are equivalent under some condition. And so that's our phase pass one. And then in pass two, we percolate this. We say we already showed that some states can never be equivalent. So B could never be equivalent to G, and A could never be equivalent to G. And that in turn means that I have two more not equivalent possibilities. So at this point, what else do you think I can rule out? So we know now E and G are not equivalent. So any box where E equivalent to G appears, that's not a possibility. So I would be in the next pass, I would be able to rule out E not equal to G. I would also be able to rule out this one. That's not going to be possible. And then anything which requires F equivalent to G also gets ruled out. So that will be ruled out. That would be ruled out. That would be the next pass. And indeed, that's what we see out here. So is that clear? Okay, so we are every pass we get some more non-equivalent states, and then that in turn sort of we keep percolating. So this kind of a multi-pass thing we end up with this. Now we end up with the situation which is basically saying B is equivalent to A if C is equivalent to D, but C is equivalent to D if A and B are equivalent. So that's good. And then B is equivalent to A if E is equivalent to F, but E is equivalent to F if A and B are equivalent. So now we have a self-consistent system. At this point, we are basically saying E and F are equivalent, C and D are equivalent, and A and B are equivalent. Right, so we have three pairs of equivalent states. A and B are equivalent. D and C are equivalent, and E and F are equivalent. If all those three terms hold, then I have a consistent solution at this point. So this is a pretty sort of straightforward process. It's going to converge. Firstly, it's a pretty efficient process, right? I mean, I obviously won't take more than my grid size is n squared, right? N squared divided 2. So it's a quadratic algorithm. In no more than n square / 2 passes, I would certainly converge, and I'll find all states which are equivalent. In this example, our states are only pairwise equivalent, but you may also end up with situations where multiple states are equivalent. So I kind of do all of that, and then we end up with this diagram. We are left with very few states at this point. And what started out with that monstrous finite state machine is reduced out here. So again, things to emphasize. Firstly, shoe states which differ in their output patterns. That is, if given a particular input value, they give different outputs, they can never be equivalent. That's a starting point. And the second observation is two states are equivalent if they give the same output that we already learned, and they go under identical input, they go to equivalent states. So that gives us this kind of a transitive requirement, and which we kind of percolate through this graph. You should be very comfortable with doing something like this, because I can assure you we'll have some question like this in the quiz. So being able to minimize things. As you can see, it's a pretty efficient process as algorithms go. It's not intractable. It's quadratic time. So systems do it. So in our finite state machine design process, this thing you will do even before you assign bits to states. Remember last time we talked about that how we do encoding of states, right? One hot coding or binary coding. But you will do this step even before doing coding. You first have to just make sure things are efficiently done. And usually we end up with these monstrous state diagrams because of the way we kind of think about these problems and all, but inadvertently we end up with states which are kind of equivalent, and so we eliminate. So let's take another example. This is a simpler example. So looking at this, do you see some equivalent state? A, B, because they have the same output and under same next state, same input, they're going to the same next state. This is, by the way, what kind of machine is this? More or Mealy? Yeah, why? Depends on the current state. If it depended on the input, I would have two columns, x equal to 0, x equal to 1, and right. Okay. So it's a Moore machine. And as we pointed out, A and B are the same because their outputs are the same. And under identical input, the next states are the same. Okay. So now what I can do is I can scratch one of these rows away. Yeah, so A and B have the same thing, so I can scratch this thing away. Okay. And at this point, B disappears, and I guess I don't know, was I using B anywhere else? There wasn't actually, so that was kind of the obvious one. Okay, so so at this point, we end up with something like this, and now we can look at it and say, okay, what's happening here? So so clearly D cannot be equivalent. D's output is 1, so D cannot be equivalent to any, but A and C are equivalent. So we are basically saying A and C are equivalent if they go to equivalent states. For x equal to 0, they both go to D, so that's great. For x equal to 1, A goes to C and C goes to A. So we are saying A is equivalent to C if A is equivalent to C. That's self-consistent, and therefore A is equivalent to C. We eliminate that, and we ended up we again kind of this thing, and so now at this point we have our state machine. A goes to it's kind of the state machine basically has two states and kind of a self loop and going to each other. So what was a 4-state machine gets simplified into a 2-state machine. Try this one. Let's look at this one. So what do you think? Any equivalent states? Anyone? So let's look at the obvious ones. States which have same output and same next states. D and G, excellent, right? So here, if you look at D and G, so I can scratch G away, and then wherever is G, I'm going to replace it with D. So wherever is G, I replace with D. I think that's all this. Okay. So now at this point, is there anything else that you think is the obvious case? Not, I mean, every next state kind of differs. So now we'll have to do our next round of pass. And we have to say, okay, let's look at possible candidates. Now, clearly, A and B can never be equivalent because their outputs differ, but A and C can be equivalent if D is equivalent to E, and C is equivalent to D, right? That's so A and B can be equivalent if D is equivalent to E and C is equivalent to D. Do you think that's possible? Because C and D have different output, and actually D and E have also different outputs. Okay, good. So that candidacy doesn't hold. What about now? Let's consider A and E. A and E are equivalent if D is equivalent to C, but that again is not possible. Their output differ, and so that's not there. What about A and F? A and F are thing if D is equivalent to F, but that's not possible because D and F have different outputs, so that's scratched out. And then finally, A is equivalent to H if D is equivalent to C, which is not possible, so that's out. So A cannot be equivalent to anything else. And you can kind of do it with that implication table that we had, that kind of a grid. I'm not going to go through the whole solution, but you can follow through something like that. So so that's kind of the idea that we can potentially reduce big state machines into considerably smaller ones. And that's the very first, after given your customer specifications or requirements, you'll create kind of your state machine, but then the very first thing you would do is something like this to kind of reduce it. And then follow the process which we had in the last class, which is assign encodings to the states and one hot or compact, something like that, and then sort of proceed with the logic. Okay, so so that's making state machines more efficient. The next thing is making sure we don't make mistakes when we are writing state machines. So oftentimes what happens is we're faced with specification and we're writing a finite state machine, but you will see that very shortly there's certain kind of mistakes that occur very commonly, which lead to a finite state machine which is not legal. Okay, so let's imagine an example that I'm creating some sort of a controller for shooting a laser gun. And this controller has a following specification. So there's a button, and we basically say that whenever we push the button, fire the laser for 3 clock ticks. And if button is pressed while laser is already firing, ignore the button. Okay. So something like that is what we are doing. So if I'm in the off state, then as long as the button, so the laser is off, so more machine, laser is off, 0, and then 3 cycles of on state, on 1, on 2, on 3. And then if I'm in the off state, if the button is off, then we stay there. If the button is on, we go to on 1, and then after that, cycle through on 2 and on 3. Okay, so if I look at the state machine, I can basically say I have 4 states. I have input B, I have output X, initial state is off. I have a bunch of transitions and bunch of actions, and in this particular case, it's a mode machine. So now let's look at given such state machines, what kind of mistakes that we make. So first thing you have to make sure is for all transitions leaving a state, that is all outgoing edges, there should not be the case that I am left with a choice. It should not be the case that for some input, I have choices of 2 outgoing edges. There should not be, the system has to be totally deterministic. If I have X, if input is 0, I should have only one choice on what to do next. And otherwise there is ambiguity. And so that's one condition. And so in other words, there should not be like a fork where I could say, oh, you can take left or right both or whatever. You can take under some condition, I can take any of these two edges. So let's imagine somewhere in my state machine, I had a fragment like this. I had a node here, and under condition A, it went to the top node, and under condition B, it went to the bottom node. The challenge with something like this is, what if A and B are both true? In that case, we are left with a choice. I could go to the top node because A is true, or I could go to the bottom node because B is true. So the way to formalize this is that if I look at the condition for every edge, which is outgoing, any two edges, their condition should be mutually exclusive. They cannot be simultaneously true. And therefore, ANDing of those two conditions should always be false. Okay, so that's another way of saying that. So A and B have to be false, right? Always false, because if for this thing to be a valid state machine. Because if that's not the case, then that means under some condition A and B can be both true. So what the change we could make is, we can say if A go up there, but go down if it is not A and B. Okay. So that way I make sure that the conditions on the two edges are mutually exclusive. So this is rule number one. Conditions associated with taking moving to a next state, moving to two different next states, they should be mutually exclusive. Second one, for all transitions leaving a state, some condition must be true. That is, if I'm in a state and I see some input, then I should know which next state to go to. You should not leave me hanging, right? I mean, it should not be the case that the system doesn't specify what next state do I need to go to. So in other words, if I look at all the outgoing edges, including self loop, then one of them must be true. So together, these things are saying one outgoing edge must have its condition true, and exactly one outgoing edge should have its condition true. So this is basically saying, let's imagine I have, let's imagine I had this condition out here saying if A go top, if not A and B go bottom, but I have left hanging, what if both A and B are false? There is nothing which is being said out there. So I need to add a condition out here about not A and not B. And that's what we do. And usually what happens is that we want to say else stay put. So in many software systems, they kind of assume that, but it's usually a recipe for mistakes also. So some systems insist that you specify all the edges. So these are two mistakes, right? One edge must be true, and exactly one edge must be true. Yeah.
Are the state machines that have ambiguity physically reliable?
No, they are not, right? I mean, because they, well, I mean, okay, in theory, you could say I can create a state machine and then I will tell it, flip a coin and decide what to do. But finite state machines, okay, so let's back up. In those of you who are computer scientists, in your automata theory class, you would see something called non-deterministic finite state machines. They are a mathematical abstraction, which are very useful at proving properties about algorithms, but hardware is deterministic. Okay, so and like even if, let's say, you were to make non-deterministic finite state machine using some source of non-determinism, it's unclear. Other than perhaps things like a lottery controller for a lottery system or something like that, probably not terribly true. So short answer, no. Okay, so let's look at an example out here. There's a digital lock, and it has, instead of numbers, it has sort of colored buttons: black, red, green, and blue. And we press these buttons, and then there is a code detector. This is some combination module, and it will send a signal unlock to a door. And this keypad talks to the code detector through 5 wires. S means black button is pressed. R means red button is pressed. Sorry, sRGB basically are indicating status of the corresponding buttons, and A means some button is pressed. Okay, so those are the 5 wires. S means this is the state of start, black one, RGB for the RGB, and A means a button is pressed, or at least a button is pressed. So, and the lock code is it's kind of a made up one. We basically say that the lock will be unlocked if I press start, then press red, blue, green, red. Okay, so red, blue, green, red is the code, and start is kind of start, right? So press start, red, blue, green, red. And then kind of the idea is that anytime a wrong button is pressed, we go back to the beginning state. You have to kind of again re-enter the code. So if I enter start, red, green, then it will go back to opening state. So what we do is we design the state machine. So the first state is the wait state. We kind of sit there. As long as the start button is not true, we keep sitting there. And then if the start button is pressed, we go to the next state, where we say, hey, start has been pressed. And then as long as no button is pressed, we stay put. If a button is pressed and it's not red, we go back to wait. And if a button is pressed and it's red, we go to the red, and we do the same thing. Okay, blue and green and red. And then here you see that we unlock the lock, and after that we go back. Okay, now I want you to look at this machine carefully and tell me what kind of problems exist out here. Slow down. Speak. Mm-hmm. Okay, but let's say the passcode is known. So I'm just talking about the technical problems with this machine. Okay, so yes, I can figure out the passcodes are true, but there's some more deep things wrong with it. It's not a valid finite state machine. So that's, yeah, okay. You want to? Yeah. Yeah, exactly. So the problem is in each one of these states, we are so right on. Let's imagine I just press all the buttons, right? So what will happen is S is pressed, so I moved there. It says A and R. R is certainly pressed because I pressed all the buttons, so it will move to red. B is also pressed, so it will move through, it will unlock the door, right? So I don't even need to decipher the code, I just press everything, okay? So the problem out here is that we are not testing for the, we are being too permissive in this process, right? So that's one challenge, okay? So we can press on. Another issue is, so that was actually the major problem, but there are also some minor problems. So when we let's see, did I mess things up? Yeah, so I think so how will we fix this thing, right? I mean, so when I'm saying go to next state when A and R is true, some button is pressed in R, I also have to say some button is pressed and it's not one of the others. Okay, so that's kind of the idea. I'm going to you'll have to modify it. You have to say it's not simply R is not pressed, but if B and G are pressed, then I should go back, right? So anytime an incorrect button is pressed, I need to go back. So I have to modify the written conditions. In our original machine, the challenge is that if B and if R, G, B were all pressed, I will take this line. But actually, if B and G are pressed, I want to take return arrow. So we do this by adding this. We are basically saying if a button is pressed and it's not R, or it is B, or it is G, you kind of go back. And I do the same changes to all the other ones. So I'm going to just skip forward. I'm going to add these conditions. So my return conditions go back to great, essentially saying if you're pressing something incorrect, you need to go back. Not simply you're not pressing the correct one. Okay, so there's a not pressing the correct one is not the same as pressing an incorrect one. So we kind of fix these. So let's say we add this. We basically modify the return this particular way. So again, hopefully you get it. So like if I'm in the green one, I'm basically saying if you get the red, you go there. But if you don't get red, or you get B or G, an incorrect one, you kind of go back. So let's say we add this. So this takes care of the problem of pressing everything together. Do you see some other issues out here? Or have I fixed the problems? Yeah, exactly. So the challenge is this naive way of thinking, I'm just going to fix back, is creating problems, which is I may have multiple things true at the same time, right? So that was one of the requirements. It should not be the case that two edges are true at the same time. And in this particular case, that possibility exists. So we are, so consider the following transition, okay? We are in start state, and we are, yeah, so let's look at A and R, and we consider its ending with this new condition that we had put. And if you simplify, you end up with that it is not mutually exclusive. So both can be true simultaneously, because I may press, if I'm pressing all of them, so R is true and B and G are true, so I could go both of those edges. So I have to replace this guy by saying I'm pressing R and I'm not pressing B and I'm not pressing G. So the condition is going to change. This A and R will become A and R and not B and not G. And I have to do the same thing. Like, for example, this guy, A and R and not B and not G. And likewise, A and G would get replaced by A and G and not R and not B. So basically, when you are making FSM, you have to firstly make sure that like it's not defeating the intent of the specification. So I know, like, going back out here, while the language then specifically said very clearly, but focus on this, unlock only when buttons are pressed in the sequence. So clearly the first attempt was not complying with the specification. So that's one part, right? Your machine should comply with the specification. And the second one is that these properties we talked about, that only one and exactly one and only one outgoing edge should be true at any time. And so one has to just make sure of that. So these are easy tests to do. Again, faced with a state machine, you should be, these are the first things you have to look. Systematically go through every state, make sure that outgoing edges, one of them is true at any time and exactly one of them is true. And the second thing you have to make sure is that your state machine complies with the specification. Sometimes the specification may require you to just exercise your common sense, right? I mean, let's say some customer gave you, going back out here, unlock when buttons are pressed in the sequence, and it skipped the word only. It probably stands to reason that, hey, it's a lock. It doesn't stand to reason that it should open for anything else. So don't be too, I guess, pedantic about specification. Apply reasonable common sense when faced with somewhat ambiguous language. Okay, so that's this kind of side. Okay, so now we have seen how we can optimize state machines, right? Reduce the number of states. We've seen that how we can make sure that they pass some basic sanity checks, right? Whether they pass the check of complying with the requirement is a trickier one. That obviously depends on the application, but the other two tests, right? I mean, making sure that outgoing edges are mutually exclusive and making sure that one of the outgoing edges is true is always to be checked. So now let's look at some examples on how do we go around designing sequential circuits. Some more. We saw some last time, so some more. So let's say we are designing a system which has one input W, one output Z, and we want output Z to be 1 if input W was 1 during the 2 immediately preceding clock cycles. So if you see out here, Z is 1 because these are 1. Z is 1 because these two are 1. And then Z is 1 because these two are 1. Firstly, looking at this, kind of seems like should be a more machine because the action is taking place in the next clock tick. So that's just a side note, but let's imagine we are designing something like this, right? So step 1, we make the complete state diagram. So intuitively, what's going on out here is, firstly, I have to keep track of, I have seen 2 1s, right? So what would be, I've seen 1 1 and I've seen 2 1s, and then the actual output thing. So kind of stands to reason faced with something like this. It's probably going to be 3 states, makes sense. So we kind of draw it like this. We call them states A, B, C. There's some name. And we basically start in the reset state. And then if I see W equal to 1, I go to B. I have seen 1 1. And then if I see one more 1, I go to state C. If I see a 0, I go back immediately to the first state and I stay put out there. And as long as I keep seeing 1s, then I keep spinning there and keep outputting 1, right? So yeah, output out there. So it's a more machine. So sort of here, if you look at like, I'll be in state C here and I'll again be in state C out here. Okay, so so in this particular case, it doesn't seem like we can optimize it anymore. I mean, the states are not equivalent, so that part is gone. So now what's the next thing that we will do? So we have the state machine. On the way to implementing it, what's the first thing I need to do now? Make it into hardware. Truth table. So I make that, right? I mean, still symbolic at this point. So I write down present state, next state, kind of create this, right? So it's basically telling me if I'm in state A, if W equal to 0, I stay in state A, W equal to 1, go to state B. If I'm in B, then W equal to 1, go to C. If I'm in C, so it's just capturing the previous thing, but states still have names, and then outputs are 0, 0, 1. Okay. So I make this table. What's next? What's the next step? What would you do next? Huh? Encode the states. Great. So we are going to encode the states. So let's say I say A, B, C are 0, 0, 0, 1, 1, 0. Okay, now remember, this is a hard problem, right? I mean, there is no efficient algorithm to tell you what the good state encoding is. If you're designing manually and you have lots of states, then one-hot coding is a convenient way. But if you are doing something more compact, it's not very convenient. So I just picked in this case 0, 0, 0, 1, 1, 0. But there are tools which have heuristic algorithms which let you figure out some good state combination. They kind of they make use of some heuristics about what states are close to each other, stuff like that. Okay, so too advanced for this course. So let's just assume that somehow we came up with this. Now, in this case, we need 2 bits. And so clearly the bit 1, 1 is something that we don't know. We don't care. It should never occur. So I put it as don't care. Now, this is a tricky one usually. So present state 1, 1, there are different schools of thoughts on dealing with it. One is we say we don't care. Another one is we basically say, if the system starts in 1-1, I don't want it to get stuck there. So I want to make sure that the next state is not 1-1. I do want it to get out of that state. So maybe I'll say, if it is in 1-1, go to A, because A is the starting state. So that could be the other school of thought. But here we have just listed it as don't care. And then this table and this table are basically just replacing A by 0,0, B by 0,1, C by 10. And at this point, I have 3 functions to implement: the function for y2, function for y1, and the function for z. So we basically systematically write down Karnaugh maps and kind of do stuff like that. And what kind of Karnaugh maps that you use depend upon the type of flip-flop you have. So we can create state machines using any kind of flip-flop. Most commonly, and the one that sort of I've been using in the lecture, is to use a D flip-flop, but certainly could be done with other type of flip-flops. So we make that. So in this particular case, the equations for y2, uppercase y2, uppercase y1, they turn out like this. And finally, output is just equal to y2. Okay, so we create that, and then finally we end up with the circuit. Now, like I said, the other thing one can do is, instead of Karnaugh maps and all, since these are small circuits, so I can use some way of making combinational logic, which is like using ROM or using multiplexer or something like that. That often is more straightforward to do. So if cost is not a consideration, like if you're using an FPGA or if you already have some ROM on your chip, one could do that. And then we do timing diagrams and all. So that kind of gives a recipe faced with any such problem. First, draw the state diagram based upon your analysis of the problem description. How many states are there? How do the states move to each other? Are there redundant states or whatever equivalent states? You kind of collapse them. Then you make the state table. At this point, the states still have names. So step 3 is give and encode the states. Then you use some tool or K-maps or something like that to create the implementation. And then finally kind of do the gates and then check. So unlike combinational logic, testing sequential logic is harder. Why do you think so? Why is testing sequential logic harder? If I give you a combination logic with 2 input and 1 output, and I give you a sequential circuit with 2 input and let's say 3-bit of states and an output, claiming that the latter is a lot harder than the former. So why do you think so? How would you test a sequential circuit? We saw a little bit of that in equivalent thing, like I said, right? We are feeding it sequences of inputs. So to test a sequential circuit, it's like let's say you made an adder. Let's say you made a 4-bit adder, adds 2 4-bit numbers, then and no carry in. Then there are basically 16 possibilities, right? 256 possibilities, and I can test for all of them. That's in theory, at least. Okay, well, so I could do that. Sequential circuit, the problem is it depends on the state which is inside. So when I said I have a 2 input, but I also have that hidden 3 bits of state. So I really need to test for sequences, all possible input sequences, and before I can be sure. So figuring out a testing strategy for sequential circuits, tends to be harder. Let me ask you a different question. Let's say I ask you, so I said, if an adder which adds 2 4-bit numbers, I can test all 256 combinations. How will you test an adder which adds 2 64-bit numbers? Anyone? Any thoughts? Okay.
Like
huh? Well, firstly, do you see a problem testing an adder which has 2 64-bit inputs? That's how many input combinations exist? 2 to the power 128. That's more than, like, even if you were, I don't know how many seconds the universe has been there, but what, 14 billion years, right? So 14 times 10 to the power 9 years. A year has how many seconds? I mean, the year has 2000 hours times, right? I mean, you can kind of multiply it out. We are many, many order of magnitude away from just number of inputs. So I can't test exhaustively. So how will you test such an adder?
In that case, I would have test cases where I just like figure like edge cases, like right over on the floor, and then I would randomly select.
Great. Yeah. Much like you do it in software, right? I mean, you test for edge cases where things are likely going to be wrong. Usually these are things like all zeros, or one party is all zeros, other party is all ones, or something like that. You test for edge cases, and then you pick some random cases to kind of do it. There are tools which help you systematically select test vectors so that they'll make sure they exercise every part of the hardware. Okay. And actually generating tests is kind of a hard problem, it's a super hard problem. Sequential circuit is even harder because I have to look at all possible sequences. So this phase, one has to look carefully and kind of figure out what is going on. There is no easy answer at, there, but when testing sequential circuit, much like when you will test for a program, you need to look for corner cases when things are more likely going to bad. Design an FSM that has an input W, output Z. Machine produces Z equal to 1 when previous two values were 0, 0 or 1, 1. So previously we had, whenever it detects 1, 1, it outputs 1. Now, if it detects 1, 1 or 0, 0, it outputs 1. So again, same process, except now things are a little bit dicier. So we have two possible situations in which we want to output 1. It's either 2 ones or 2 zeros. So usually when faced with this problem, the way I like to approach them is I think of what are the different cases. So one case is 0, 0. I race through that. And then I stay there as long as I keep getting zeros. And the other one is 1, 1. And I stay put out there. So I first draw the backbone of my state machine. And then I look for other cases. So then I say, okay, I started out here. 0 took me on that path. 1 took me on the bottom path. Now, if I'm in this state, right, I've seen 1, 1. If I see a 0, I go here, right? Because there's a possible start of a 0 sequence. If I get a 1, I go out here. And likewise, this one. And then likewise, if I'm out here, and if I get a 1, I get to D, and so on and so forth. Do you see something interesting about A? What is interesting about state A out here? You never go back to it, right? I mean, so occasionally you will see these kind of state machines where I never go back because it just serves the starting purpose. Yeah. I mean, in a way, yeah, it's a waste of a state because after that initial thing is never being used. Yeah, so it's a pity, isn't it? Right? Because if I could do it in 4 states, I could get away with 2 bits instead of 3 bits at least, right? So absolutely good question. Do you think you can do something about it? Unfortunately, not. Yeah.
Can't you replace A?
No, you can't. If you replace A with B, that means you're saying A and B are equivalent, right? But that's not. Yeah, sure. If someone tells you first input is 0, then always 0, then I have to solve the problem. But in this case, the first input could be 0 or 1, so therefore I don't have any chance. So at least the way the problem is stated, you can't do it in less than 5 states, and your observation is right on that I'm needing this extra state bit just because of that input. So yeah, unfortunate, but that's the way it is. And then again, we walk through the same steps. We first, so firstly, again, convince yourself there is nothing to optimize out here. There's no equivalent states. I create a symbolic truth table. I'm going to flip through it rapidly again just to show the steps, right? I mean, again, it's a more machine. Now I assign the states. So I have 5 states, so I need at least 3 bits. So there are going to be lots of unused bits out here, right? Three states are not used. So I create this kind of a thing, and then I write down, create the expressions again using some tool. So faced with this insight that I never go back to state A, other than when we initially start out with, it may turn, usually for something like this, some sort of a state assignment which is clever can reduce the hardware. Okay, so one have to kind of play with it a little bit. So in this case, it turns out if I assign the state this particular way, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0, I get a lot more complicated thing. If on the other hand, what I do is I assign state A to be all 0 and B, C, D, E, the remaining state, to have the first bit to be all 1. If I do that, I have a much simpler solution. So I'm not going to again show like precise details, but this is why state encoding matters, right? I mean, one state encoding gave me these equations, and the other state encoding gives me these equations. Clearly much better with the latter. So state encoding matters, and sometimes insight, like looking at the problem, some structure in it can help you. Of course, software tools can do it for you. Unfortunately, this type of problem state assignment is not something you like. Logisim doesn't do it for you, so there's no like low level tools which can handle that for you. Okay, so state assignment matters. Now there is an easier solution out here also, and this involves thinking in terms of, it's like in software parallel programming, right? If I don't, do they teach parallel programming in 31, 32, 33? Okay, so only those have done 33. So sometimes problems become easier where instead of saying there is a single FSM doing my task, I have multiple FSMs doing different parts of the task. In this case, the problem stated that I want to output 1 if input is preceding 2 inputs are either both zeros or both ones. So one way we can approach it is we can say, look, there is 2 worker FSMs. One is tasked with 0, 0, and the other is tasked with 1, 1. And those FSMs are super simple to implement, it turns out. And then my overall machine is saying output Z is if either one of them says true. Okay, so I make Z equal to this. Now, technically, it is no more a single FSM because there are 2 FSMs doing the job, but the overall system is still finite state, right? And it will still do the job correctly. So it kind of meets the notion of what we are doing. It has, what's the disadvantage? Well, if you look at this one, each one of them needs 2 bits of state. So I need total of 4 flip-flops instead of 3 flip-flops. But I'm saving considerably on the combination logic parts. It's probably okay. Sometimes you may be told, oh, you can't do this. Then it's a different story. But otherwise, yeah, it's a reasonable way to kind of work with. So actually, that also brings to me another thing that another approach to pattern detection type problems. And they work like the following. Let me see if I can add a slide out here. Okay. So let's say I tell you there's a stream of characters coming in, and I want to detect the word, I don't know, mama. Okay, let's say I want to detect this. I want to detect this. Okay, so I can create a state machine and detect M, A, and kind of do, right? I'm in classical way. But there's a, for these kind of problems, right? I'm detecting these patterns. Another way I could do is the following. I can create a chain of flip-flops. Now, what will happen? Let's imagine the characters are coming this way. And let's say the first X came, then Y, then M, A, right? What will happen is first X will come here, then X will move out here, Y will come here, then X will move out here, Y will move here, M will come here. If I'm looking in time, right? So X came, then Y, then M, then A, then M, then A. At some point, I will have M sitting here, I will have A sitting here, M sitting here, A sitting out here. Right, for a transitory moment. If there is a pattern, the rightmost flip-flop will have the oldest value, and the leftmost flip-flop had the latest value. And then what I can do is I can take these and then feed it into a combination logic, which basically has some comparator. And then this looks at, oh, is this guy M? Is this guy A? Is this guy M? Is this guy A? And then AND them together. So I can put a little comparator equality checker, put M here, put A here, put M here, put A here, take their output and feed them into an AND gate and take its output. And now I have my pattern detector. So this kind of a chain of inputs approach, right? I mean, I can always detect any pattern with it. The problem with though is that depending on the problem, this might be huge. Like, I mean, I may have to look at large numbers. So this is, but usually for looking for a specific pattern, this kind of thing can that work. In software terms, it's basically I'm maintaining an array of recent values and then working off that. So just wanted to mention that for sometimes like that particular problem where I'm looking for 0, 0 or 1, 1 can be done very easily this way. I can basically, so let's see how that problem we will do. Right, so our problem was to look for most recent values are either 0, 0 or 1, 1. So what I'll do is so what's going on out? My input is coming here. First flip-flop, its output would be input as it was 1 clock tick ago, right? So let's say I call this thing input at time t. Then this is input as it was at time t minus 1. And this is input as it was at time t minus 2. This AND gate is basically detecting the pattern 1, 1. And this NOR gate is detecting the pattern 0, 0. And then this OR gate is saying either one of them is true, then my output Z equal to 1. So I can implement a lot of pattern detectors by this kind of an approach where we basically put a chain of flip-flops. This is often also called a shift register, because kind of the inputs are kind of shifting, but it lets me remember the most recent some k inputs. And then as long as I can solve my problem using those efficiently, then it's good to go. Not all FSMs can be done efficiently in this manner. Like, for example, remember I had this problem like output a 1 if the number of ones thus far is even. That I cannot solve this way, because to keep track of number of ones or even thus far, I'll need to know all the inputs thus far. So I can't solve that kind of problem this way. But any problem, any FSM problem, which only requires me to look at most recent some k inputs, where k is known and fixed, I can solve them in this particular manner. So yeah, just something not always efficient, but if you are looking for a quick and dirty solution, this kind of works off. Okay, so final thing on this FSM story. Oftentimes, we need to bring a sequential circuit to a known state because we are resetting it. If we had seen it in our traffic controller example, where kind of the idea was, if reset comes, we immediately go to that state where north-south direction was green. So usually in our systems, we have, like, when hardware powers up, then there is some sort of a special circuit which detects that power up has just happened, and it sends out a signal to all the rest of the hardware saying, hey, there is a reset. And usually, if you look at the data sheets, they kind of give you very detailed descriptions about how to generate a reset pulse for the hardware. So like processors and all have that. Sometimes you may have a reset button, okay, like press it and the hardware gets reset. Sometimes there is also something called a watchdog timer. So power up circuit, reset button, or watchdog timer. So what's watchdog timer? Oftentimes what happens is software hangs. Faulty software, buggy software, it just hangs. So what happens is that those people who do hardware, they know that software is often buggy, so they put some protection mechanism in hardware. And one of the mechanisms they put is there is a timer, and if the timer fires, like some time has passed, then it's going to forcibly reset the hardware. And kind of the idea is that the software should periodically go and restart the timer. So in the software, there would be some place where it says, I'm going to start this watchdog timer, and I know this watchdog timer will fire in whatever 1 minute. And so I better make sure that I go and restart the timer, reset the timer before 1 minute is up. And if the software fails to do it, then the hardware will reset the hardware. And so it's called watchdog because the timer is basically saying, hey, the software didn't hang. And kind of the idea is that the software hung, then it will fail to reset the timer, and therefore that's. So many processors, if you look, they actually have this watchdog timer inside them. Arduinos, for example, if you click with them, have that. So how do we, so there are all of these possibilities: power up circuit, reset thing, watchdog timer, and they send out a pulse. And when the pulse comes, I want to move to the reset state, okay, the start state. So how do we do it? Well, this is where the flip-flops have some special support for it. So if in LogicSim, the flip-flops have set reset. I mentioned this earlier also, that flip-flops have SNR set reset capabilities. So there are a couple of ways to sort of potentially do it. One is get a flip-flop which has the ability to do set and reset. Sometimes the flip-flops have asynchronous set reset, which means whenever the signal comes, they immediately set and reset. It's almost like separate from the clock. And another possibility is that the flip-flop has synchronous set and reset, which is when the signal comes, then it waits until the next clock edge. So one can do that. But let's imagine I do not have a flip-flop with a set and reset, right? So if I have this, where reset is there, I can use that. But let's say I don't have this. Then you can always make your own. Let's say I only have ordinary D flip-flop and I want to add to it a reset signal. All I have to do is I have to put an AND gate like this. The D input feeds to the AND gate and my reset, N means negative. So it says reset if low. So idea is whenever reset is low, then at the next clock tick, the flip-flop will reset. So I can always make reset or set by adding my own combinational logic around it and just have a pure D flip-flop as needed. So yeah, just wanted to mention that either you can have flip-flops which come with built-in, or we can make our own. So yeah, synchronous set and reset or have the disadvantage that they take time. On the other hand, the advantage is we know that things are happening at the clock tick. So that's positive. I've kind of listed some other stuff. Asynchronous has the advantage immediately it resets. I don't have to wait for the clock, and there is a few reasons why we might want to do that. Disadvantage is if there is a little bit of a spike because of noise on my reset signal, my flip-flop will get reset. So that's dangerous. Now, one reason why asynchronous often is useful is when the system starts up, if you look at its early behavior, power supply takes some time to build up, but so do clocks. Clocks don't start immediately. They take maybe 5-10 milliseconds to start up. So there's a while during which your system clock is not very stable. And during that time, funny stuff can happen. So again, asynchronous reset sort of tends to be helpful. So yeah, I mean, you'll find both, and kind of there's no hard decision between one or the other. Asynchronous reset is also pretty common. D flip-flop in Logisim has asynchronous set and asynchronous reset. They don't have synchronous. So if you want synchronous, you'll have to build using your own logic. Cautionary notes. When you look at the flip-flop symbol, there's no explicit whether the set or reset are synchronous or asynchronous. There is no particular symbol to differentiate. So one has to read the document to understand. And the other thing I would mention is sometimes you will see flip-flops which, instead of working on edges of clocks, they work on levels of clock. So they will say, whenever clock is 1, the flip-flop does its job. Those technically are what we will call as latches, D latches. And I have not talked about how to design using those, but there are real circuits where they get used. And this topic for some other course that you might take. Just cautionary note again, Logisim D flip-flops can be set to be level sensitive also. So they are powerful. You can go to the clock input and you can say rising edge of clock or falling edge of clock or clock equal to 1 or clock equal to 0. I have not talked at all about how to design using these. They require some more thought and care. So finally, to close out this module, types of flip-flops. Yeah, so we have seen D flip-flop, right? So clock edge comes, whatever is on D gets inside the flip-flop, and Q, the output, represents the content of the flip-flop. So this is the most common flip-flop, most common. But there are some other flip-flops also, and there is one called T flip-flop. And what it does is, if T is high, then the flip-flop flips its value. 0 becomes 1, 1 becomes 0. So in other words, the new Q is the negation of the old Q. And if T equal to 0, then Q holds its value, right? So that's the T flip-flop. We'll come back shortly to this. There's something called JK flip-flop, where it has 2 inputs, J and K. And if both are 0, flip-flop remains unchanged. If K is 1, J is 0, flip-flop resets. If J is 1, K is 0, flip-flop sets, and otherwise it toggles. And then finally, there's something called SR flip-flop. Now, let's ignore that for the moment. let me ask you the following. Do you think can I implement a T flip-flop using a D flip-flop? So in other words, can I do the following? So I'm giving to you a D flip-flop, right? And this thing does the following. What I want is a T flip-flop. So let's imagine I want a bigger system. It has an input T and output Q. And I want the behavior to be I want this behavior. So I want to create a bigger system where input T would cause the output of this dotted system Q to be such that if T is 1, it's the old value of Q negated, otherwise the same value.
Or XOR the input the T with the old Q, right? Like if T is 0 and you have old Q is 0, then it stays 0. If Q is prime, T is 0. Q remains.
Good. So you're right on. So the suggestion that he has the following, that I can put an XOR gate out here. Sorry, bad handwriting. T goes into this. And then what you want is, if T is 1, I want it to toggle. And if T is 0, I want it to be stable. So I can take this Q and feed it to this XOR gate, and that will do the job, right? Because XOR is a conditional inverter. So I could do it that way. Or alternatively, this is nothing but a finite state machine problem, right? It's a state machine which has 2 states. So you can, right? Q can be 0, Q could be 1. So 2 states. Let's call them 0 and 1. And if I'm in state 0 and T is 0, then I stay put. If I'm in state 1 and T is 0, I stay put. And otherwise, I transition. And then you can follow the methodology that I'd given previously to make, which was using D flip-flop. You can now implement a T flip-flop using that. So these flip-flops themselves are just finite state machines, and I can express it this way. What about JK flip-flop? Let's look at JK here. So what would be the state machine for JK? How many states are there in JK flip-flop? Even how many states are there? It's a flip-flop, 1 bit, 1 state. Sorry, 2 states, 1 bit, 0, 1, right? So 2 states. Under what conditions do I? So if I'm in state 0, that means Q is 0. Under what condition next state is also 0? So if you look out here, if Q is 0, then either JK are both zeros, I stay put, or JK are 0, 1, then I stay put. And therefore, I stay put if it is not J. What about 1? If I'm 1, I'm and then I will stay in 1 if I'm in either here or this situation. So I stay put out here if it is 1 0 or 0 0, and that means I put here if it is not K. And then I'll let you figure out when do I move. So I can think of these flip-flops as state machines and kind of solve it this way, or we can do it by intuition the way you kind of did. So there are all these different kind of flip-flops, but they're mutually substitutable. Usually in libraries, you will only find the D flip-flop, but the others also exist. Okay, I already covered this, so that chain of flip-flop approach that I had mentioned. So let's take another example of this approach. Let's say I were to tell you that generate an out. So you are getting some numbers, and I want you to output a 1 if there is a peak. So what I mean by that is the middle number. Basically, I'm seeing 3 numbers where the oldest number and the newest number are smaller than the middle number. Okay, so basically saying xt, the latest number x, is smaller than the previous number, but the previous number is greater than the next oldest number. So one way I could approach this thing is I could basically say, look, if my numbers are in this case, we are saying 2-bit inputs, so 2-bit numbers, I could basically say that, look, let me consider all possible states. There are total of, I will need to know 6 bits, 64 states, too much work. But I can solve it using that approach where I basically take 2 2-bit flip-flops, make a chain of them, and then use comparators here, followed by an AND gate, and solves the problem. So these comparators are checking for these 2 conditions. One is checking for this condition, the other is checking for this condition, and then I have an AND gate. So for many problems, this approach is a lot easier to do. It still needs 6 flip-flops. So still have 64 states, but lot more painless to do than drawing finite state machines and all. So so one could, if you proceed with this approach, there are ways in which you can simplify the problem by reducing the number of states and all, but generally you will find kind of just making it like this is a lot easier to do. What else? I think this is mealy more. We have seen it quite a bit. One thing I just want to mention is mealy and more are equivalent in the sense that whatever you can do with mealy, you can do with more. Whatever you can do with more, you can do with mealy. If you don't worry about when the output appears relative to the input, that's a big caveat. So the output in case of more would be generally slightly delayed, and therefore that's something to keep in mind. Generally speaking, mealy may require fewer number of states. So that's so previously we have talked about mealy are faster to react. That's an advantage. But they also may require fewer states, but their combinational logic may be more expensive. So mealy is kind of it's a tough call. If you are in the software world, probably the difference doesn't matter as much, but on the hardware world, things do matter. So there are ways in which you can go from mealy to more, and you can go from more to mealy. Kind of generally speaking, the approach works like the following. This is not something that one has to do very commonly, but oftentimes you do face this issue. I'm given a Moore machine and I want to come up with a mealy machine which will produce the same output sequence given the same input sequence, modulo the fact that the timing would be different. So basically what we do is the following. So what we have here is we create let's see, we are this is a error. So we are given a Moore machine and we want to go mealy. Now you might argue Moore is just a special case of mealy, so why do I want to do it? But the reason being that I may, by doing it, I may have fewer number of states. So the way we kind of work is the following. We first write down the truth table for the Moore machine. So this we have seen many times. Given state graph, I can create this. The next state depends on the inputs, but output is independent of the state. So I create this. And then what we do is we create this output. So we form the state transition graph with output now written in this manner. So what we are doing is the following. Here the output was separate column, but what we now do is we write this tuple. Let me. So we are going to write a tuple out here, next state and output. So this column, this box out here, we have X and we have 0. So we write X comma 0. Here, when n equal to 1, make sure. Yeah. So let's back up a little bit. So remember, in mealy, the output depends on the current state. So we look at the state X. If I'm out here, X and input is 0, next state is X, and in that next state there would be some output. So output whenever we are next state X is 0, so I put X equal to 0. Here, when n was 1, and I was in state X, next state is Y, and my output is the output corresponding to Y. So I create this mealy state graph where I put the next state and I put the output which would occur in that next state from the Moore machine. Another example, if I'm in Z and n is 0, the next state is Y, but the output in Y is 1. So I put that out. This is the new mealy state diagram that happens. This basically saying I'm in a Moore machine, but the output is now looking ahead. It's the output of the next state. And that gives me a mealy machine, and then I kind of give the diagram. So I can always go from Moore to mealy in this particular manner, and then implement it. Converting mealy to Moore operates in kind of a similar manner. I'm going to skip this one and come to it later. The thing, so there was a question on Piazza, why do we pick mealy? Why do we pick Moore? So we now see a few reasons. So one is mealy reacts faster. Second is mealy can have fewer states. So sometimes that can make a difference. But perhaps the most crucial reason is in case of mealy, in case of Moore, the output comes directly from the state register. It doesn't depend on the input. So there are no glitches that can appear on the input and make it the output. So it's just a more robust design. It does not matter in software at all. In software, there is no glitches, but in hardware, glitches matter, and therefore there's a strong bias in favor of a Moore machine in hardware. That this kind of circuit at the output is cleaner for a downstream user to have that. Now, having said that, there is still a problem. Do you think in a circuit like this, where registers are going into combinational logic, and then that is what is going to output, do you think we can still have glitches? So clearly in melee, I can have glitches. My input can go through, and so any glitch on input goes to glitch on output. What about this design? Can I still have glitches like this?
With the state register, it'll just be delayed by itself.
Okay, so let's imagine state registers output change their output at the same time. So I have output combination logic whose inputs are changing at the same time. Do you think we can still have glitches at output? So if you go back when we had talked about Carnot map and we had talked about the hazards, then if I have different paths through my combination logic and if they have different delays, I can always have glitches. So more design are safer, but not fully safe. So what do we want in that case? What we really want is my output to come directly from the state registers, no combination logic. That would be the ideal situation to have. And in that case, there's no combination logic, so I don't have to worry about hazards. So there are two ways one can approach this thing. One is called pipelined melee. And basically what we do is we just slap some registers at the output of a melee machine. So we take our melee machine, which is this guy, and we just put some registers out there. All the outputs are now coming from a register. What happens now? My outputs are all delayed by one clock tick, right? It's a melee machine, but I've added, hopefully one thing all of you have realized is flip-flop delays a signal to the next clock tick. So the output of a flip-flop is the signal as it was at the last clock tick. So these output registers are just serving to delay things. So in this case, my output here will have no glitches, but it's delayed by one clock tick. Let's say in this design, let's say I had 5 bits of state registers. Let's say this was 5 bits. And let's say I had 3 outputs. Let's say it was 3 bits. How many states does this system have? This top design. So I took a melee machine with 5-bit state register and I added, and it had 3 outputs. So I added 3 flip-flops at the output to get my property that all outputs are coming from some flip-flop. How many states can this upper design have? How many flip-flops does it have? 5 plus 3, 8 flip-flops. If you have 8 flip-flops, how many states can we have maximum? 2 to the power 8. So 256 states. So whenever you're adding these registers, you're adding state. Okay, it's just that we are calling them output registers, but they're still state. All flip-flops of a system are part of the state. And normally, like let's say I have a system with 100 flip-flops, then it could be in as many as 2 to the power 100 possible states. It's possible that not all states may be reachable, in which case we discount them. But if they are reachable, then they're part of the system. So that's one approach. The upper approach is take melee and put registers at the output, and now no glitches. There is another strategy, which is pipeline more, which I take a more machine and then do the same game. Except now my outputs were already delayed and I'm delaying them one bit more. So this kind of machine where taking more machine and adding registers is now making my design sluggish by 2 clock ticks. Input effect will be felt at the output after 2 clock ticks. So not very desirable. So this is not very useful. This one, okay, I'm no worse than what my Moore machine was doing. But there is a clever trick that often is used is you store outputs in the state. So kind of the idea out here is the following. I'll say, okay, so if I have an output called Z, then let's assume that this Z is coming from one of the state bits. So I'm going to encode my state bits such that one of the state bits is the same, is always the same as Z. And this solution is called output coded more. And so let me see if I have an example. I don't have an example, so let me see if I can pick up an example from earlier on to argue how that might work. So give me a moment. Yeah, let's look at this design. This was already. Okay, so let's look at this design. This was an older machine, and I had an output, and it has 0, 0, 1, 0, 1. That's the output. And if I look at my state registers, present states, if I look at first bit, it's 0, 0, 0, 1. So y3 is not equal to Z. What about y2? Y2 is not equal to Z, and y1, they are not. So none of the state bits are the same as Z. So in this case, Z requires some combinational logic on top of y1, y2, y3, and indeed we had this equation. But we had this other design where Z was again 0, 0, 1, 0, 1. But if you look at bit number y1, it too is 0, 0, 1, 0, 1. And therefore Z was equal to y1. So the state register bit y1 is the same as Z. So in this case, Z is coming directly from a state bit. No extra register needed. So if I encode my state bits cleverly, I can make sure that output is equal to one of the state bits. Each output corresponds to some state bit. And that way we can achieve the desired property that my outputs are coming from a state register. So that's kind of the final thing. Oftentimes, again, for good hardware design, we end up doing that. So something to kind of keep in mind. So these were all implementation issues. Again, finite state machine is a concept existing in software and hardware both, but in hardware, the distinction between milli and more and where is the output coming from becomes super important. So to summarize these things, then we have sequential logic, kind of how do we go around designing it. Today, we saw a few important things. Firstly, when you're designing finite state machine, you have to be careful to get it right. Don't make mistakes about the edge structure and all. We also have to make sure that assigning bits to states, that encoding, there are lots of issues out there. Some approaches are easier for human design, some are harder, some result in better behaved output than others. So one has to kind of account for these kind of things. So again, nowadays tools do this kind of design. This is obviously a lot more complicated, but oftentimes this is one kind of stuff where you may still have to intervene manually because tools often don't do that great a job. But it's good to know kind of what's going on under the hood. So that's sequential design. Next time around, what we are going to do is to go where we combine finite state machines that we have seen together with things like adders and stuff like that we have seen. We are going to look at designs where FSM like this, these coexist with complex combinational models. Okay, so that would be the topic next time around. I'm going to stop here.